You're floating in the darkness of space, and ahead of you there's nothing. Not the kind of nothing you see when you close your eyes at night. Not the darkness between stars. This is something else entirely. A region where light itself goes to die. A black hole. And somehow, impossibly, you're drifting toward it. The question isn't whether you'll fall in. That decision was made the moment you crossed an invisible boundary you never saw coming. The question is, how long do you have? How long until the point of no return? How long until your body is pulled apart, atom by atom? How long until you cross the threshold where even light can't escape? This isn't a hypothetical exercise. Right now, at the center of our galaxy, there's a supermassive black hole called Sagittarius A star, waiting with the patience of something that has already won. It's consumed millions of times the mass of our sun. It's been there for billions of years, and if you were falling toward it right now, you'd have a very specific amount of time left. Not forever, not instantly. A countdown measured in hours, minutes, and eventually fractions of seconds. Most videos about black holes focus on what they are or how they form. This one asks a different question. What's the timeline? If you started falling right now, what happens in the first hour, the first minute, the final second? Because falling into a black hole isn't an instantaneous event. It's a journey with distinct phases, each one more irreversible than the last. And the clock starts ticking long before you realize you're falling. Let's establish where you are. You're not near the black hole yet. You're in what astronomers call the safe zone, a region where the gravitational pull is strong, but not catastrophic. Maybe you're in a spacecraft that's experiencing engine failure. Maybe you're an astronaut who's been separated from your ship during a deep space mission gone wrong. The specifics don't matter. What matters is that you're approximately 1 million kilometers away from the event horizon of a stellar mass black hole. Let's say 10 times the mass of our sun. 1 million kilometers sounds like a safe distance. It's more than twice the distance from Earth to the Moon. But in the gravitational landscape around a black hole, distance means something different. You're already inside what's called the sphere of influence, the region where the black hole's gravity dominates everything else. The moment you entered this zone, your trajectory changed. You might not feel it yet. Your body registers no sudden shift. But the mathematics of your path has already been rewritten. At this distance, if you had a working thruster system, you could still escape. You'd need to fire your engines with enough force to reach escape velocity, and for a black hole of this size, that's roughly 40% the speed of light. That's 120,000 kilometers per second. Your spacecraft can't do that. Nothing humanity has ever built can do that. So the window for escape has already closed, practically speaking, but theoretically, you're not yet doomed. Not technically, not for another few hours. This is the first phase of your fall, the deceptive calm. You're drifting. The black hole is invisible to your eyes. It emits no light by definition, but you can see its effects. Any dust or gas in the area is being pulled inward, forming a glowing accretion disk that spirals around the event horizon like water circling a drain. The disk is bright, almost blinding, heated to millions of degrees by friction as particles collide at relativistic speeds. The light is blue-shifted toward you and red-shifted behind the black hole, creating a distorted halo that doesn't look like anything you've seen in astronomical images. It's asymmetrical, warped, alive with motion. You check your instruments. Your altitude is dropping. Not quickly. Not yet. You're falling at about 50 kilometers per second. That's fast by human standards. It's 180,000 kilometers per hour, more than 100 times faster than a bullet. But in cosmic terms, it's gentle. At this rate, it would take you about 5.5 hours to reach the event horizon. 5.5 hours. That's how long you have left before the point of no return. Less than a workday, about the length of a flight from New York to London. You could watch 2 movies, you could read half a book, and at the end of that time, you would cross a boundary from which there is no reversal, no escape, no second chance. But here's the strange part. You don't feel like you're falling. There's no wind, no sense of acceleration. In free fall, you're weightless. You float in your spacecraft, or in your spacesuit, if that's all you have, exactly as you would aboard the International Space Station. Gravity is pulling you downward, but it's pulling everything around you downward at the same rate, so relative to your immediate environment, you feel nothing. This is what Einstein meant by the equivalence principle. In free fall, you can't distinguish between floating in deep space and falling into a black hole. Not yet. Your body doesn't know it's dying. Not for hours. Let's talk about what's happening on Earth while you fall. If you're able to transmit a signal back home, a distress call, a final message, it will take time for that signal to arrive. Light travels at 300,000 kilometers per second, so if Earth is, say, 10,000 light years away, your message won't arrive for 10,000 years. By the time anyone receives it, you'll have been gone for 10 millennia. But let's assume you're closer. Let's say you're only 1 light hour from the nearest human outpost. Your message will take 1 hour to arrive. You send it now. I'm falling toward a black hole. Estimate 5 hours until I reach the event horizon. 1 hour later, the people at the outpost receive your message. They respond immediately. Hold on, we're calculating a rescue trajectory. But their message takes another hour to reach you. By the time you receive it, 2 hours have passed. You're now 3 hours from the event horizon. Your speed has increased to 80 kilometers per second, and the reality is setting in. No one is coming. There's no thruster powerful enough to catch you, no tether long enough to pull you back. The people who care about you will spend the next few hours watching your telemetry, knowing exactly when you'll cross the threshold and being completely powerless to stop it. This is the psychological weight of the countdown. It's not instant. It's not a surprise. You have time to know what's coming, and that might be worse. At the 3-hour mark, something changes. You're now 540,000 kilometers from the event horizon, about 1.5 times the distance from Earth to the Moon. Your speed is increasing, not because you're using engines, you have none, but because the gradient of gravity is getting steeper. The closer you get, the harder the pull. And now, for the first time, you begin to feel something. It's subtle. A faint tightness in your legs, a slight stretching sensation along your spine. If you're falling feet first toward the black hole, the gravitational pull on your feet is stronger than the pull on your head. This difference is called tidal force, and it's the signature of a black hole's lethality. Right now, the difference is barely perceptible, maybe a fraction of a percent. But it's there, and it's growing. You're being stretched. The technical term is spaghettification, and yes, that's the real word astrophysicists use. Your body is being turned into a long, thin strand by the differential gravity, but not yet. Not at this distance. For now, it's just a whisper, a preview. Let's pause here and talk about what kind of black hole you're falling into, because the timeline changes dramatically depending on the mass. If this is a stellar mass black hole formed from the collapse of a massive star, it might be 10 to 20 times the mass of the Sun. Its event horizon would have a radius of about 30 to 60 kilometers. For a black hole like this, the tidal forces become lethal long before you reach the event horizon. You'd be ripped apart while you're still thousands of kilometers away. Your 5-hour countdown would end not at the event horizon, but at a point called the spaghettification radius, where the tidal forces exceed the tensile strength of human tissue. But if you're falling into a supermassive black hole like Sagittarius A star at the center of the Milky Way, which is 4 million times the mass of the Sun, the event horizon is enormous. It would have a radius of about 12 million kilometers, roughly 17 times the size of our Sun. And here's the counterintuitive part. Because the event horizon is so large, the tidal forces at the event horizon are actually quite gentle. You could cross the threshold intact, alive, conscious. You wouldn't be ripped apart until you were much deeper inside, closer to the singularity. For this script, let's say you're falling into a supermassive black hole. It gives you more time, more phases, more countdowns within the countdown. So, you're 3 hours from the event horizon of a supermassive black hole. You're falling at 80 kilometers per second. The tidal forces are noticeable, but not yet dangerous. And ahead of you, the accretion disk is getting brighter, closer, more chaotic. You try to look behind you, back toward the direction you came from. But something is wrong. The stars look distorted. The constellations you know are bent, stretched, pulled into strange arcs. This is gravitational lensing. The black hole's gravity is bending the light from distant stars as it passes by. The entire sky behind you is warped into a funhouse mirror, and directly behind the black hole you see something impossible, a bright ring of light where no light should be. This is the photon sphere, a region where light orbits the black hole trapped in circular paths. Some of that light is escaping and reaching your eyes, creating a glowing halo. You're seeing the universe the way no human has ever seen it, and you're seeing it with 2 hours and 59 minutes remaining. The second hour passes in silence. You've stopped checking your instruments. The numbers don't matter anymore. Your speed is 120 kilometers per second. The tidal forces are stronger. Your spine aches. Your legs feel heavy. Your head feels light. The stretching is real now. You curl into a fetal position, trying to minimize the distance between your feet and your head, trying to reduce the tidal gradient. It helps, but only slightly. The accretion disk is close now. You can see individual streams of matter spiraling inward, glowing filaments of ionized gas, probably the remnants of a star that ventured too close 1,000 years ago. The disk is loud. Not in the way sound travels through air, there's no air here, but your instruments pick up electromagnetic radiation across the spectrum, X-rays, gamma rays, radio waves. If you could hear it, it would be a roar. 1 hour remaining. You're 180,000 kilometers from the event horizon. Your speed is approaching 200 kilometers per second, 2/3 the speed of light. Time is beginning to dilate. You know this intellectually. Einstein's general relativity predicts that time runs slower in strong gravitational fields, but you can't feel it. Your watch still ticks at the same rate. Your heartbeat still feels normal, but if someone were watching you from a safe distance, far from the black hole's influence, they would see your clock slowing down. For every second that passes for them, less than a second passes for you. This is the beginning of the strangest part of the timeline. the disconnect between your time and everyone else's. To you, you have 1 hour left. To an outside observer, you have much longer. In fact, to them, you will never actually reach the event horizon. They'll watch your image freeze, redshift, and fade as you asymptotically approach the boundary, getting closer and closer, but never quite crossing. The light from your body will take longer and longer to escape the black hole's gravity, stretching the wavelength until you disappear into infrared, then radio waves, then nothing. But from your perspective, the countdown continues. 59 minutes, 58, 57. The tidal forces are no longer subtle. Your spine is screaming. The difference in gravitational pull between your feet and your head is now strong enough to cause real damage. If you're in a spacesuit, the suit's pressure might be keeping your blood from pooling in your lower body, but it won't stop the stretching. Your bones are creaking, your joints are separating, the pain is extraordinary, and yet you're still alive, still conscious, still falling. 30 minutes remaining. You're close enough now to see the event horizon itself, or rather, the absence of it. It's not a surface. It's not a membrane. It's a point in space-time where the escape velocity equals the speed of light. From the outside, it looks like a perfectly black sphere, darker than the space around it, surrounded by the blazing accretion disk. But as you approach, it doesn't look like you're approaching a wall. It looks like the universe is closing in around you, the stars compressing into a bright ring behind you, while the darkness ahead expands to fill your vision. 20 minutes. Your body is failing. The tidal forces are now stronger than the structural integrity of human tissue. If you're falling feet first, your legs are being pulled away from your torso. The bones in your ankles snap first, then your knees, then your hips. You're being disassembled, joint by gravity alone. The pain is beyond description, and yet your brain is still functioning. You're still conscious. The human body is resilient in ways evolution never anticipated. 10 minutes. You're 60,000 kilometers from the event horizon. Your speed is 260 kilometers per second, 87% the speed of light. The light from the accretion disk is blue shifted so severely that it's no longer visible to your eyes. The ultraviolet radiation is cooking you, even through your suit. But it doesn't matter. The tidal forces will kill you long before the radiation does. 5 minutes. Your body is no longer recognizable. You've been stretched into a thin stream of atoms, a column of matter falling inward. Your head and your feet are separated by kilometers now, but the neurons in your brain might still be firing, clinging to the last moments of consciousness. Or maybe not. Maybe you died 10 minutes ago, and only the cells remember. 1 minute. 1 minute remaining. You're 12,000 kilometers from the event horizon. Your velocity is 285,000 kilometers per second, 95% the speed of light. At this point, the classical physics your body evolved to understand has completely broken down. Time, space, and causality are behaving in ways that contradict every intuition you have. But let's be clear about something. You're almost certainly dead by now. The question is whether any part of you, even a fragment of consciousness, a final electrical impulse across dying neurons, experiences what comes next. For the sake of this timeline, let's assume something miraculous. Let's assume you're falling into an even larger, supermassive black hole than we initially described. Not 4 million solar masses like Sagittarius A star, but 4 billion solar masses, the kind that lurks at the center of giant elliptical galaxies. At this scale, the event horizon would be so enormous that the tidal forces at the threshold would be gentle enough for a human body to survive crossing it. You'd die later, deeper inside, but you'd cross the point of no return intact and conscious. This is the only way the final phase of the countdown makes sense from a first-person perspective. So, let's revise our scenario. You're falling into one of the universe's largest black holes, and you're about to experience something no human observer will ever witness: the view from beyond the event horizon. 30 seconds. The universe behind you has compressed into a shrinking circle of light. Every star, every galaxy, every photon that's ever traveled through space is being blue-shifted and concentrated into a smaller and smaller region directly behind you. It's impossibly bright. If your eyes still function, the intensity would blind you instantly. The entire electromagnetic history of the universe is being funneled into your final line of sight. And ahead, pure darkness. Not the darkness of a closed room or a moonless night. The darkness of a region where no light has ever existed and no light will ever escape. You're staring into the void that defines the word 20 seconds. You cross the photon sphere, the region where light orbits the black hole in unstable circular paths. For a brief instant, you could theoretically see the back of your own head, light from your body having circled the black hole and returned to your eyes, but you don't. The photons are too scattered, too redshifted, and your eyes are likely no longer functioning anyway. 10 seconds. The event horizon is 3,600 kilometers away. You're traveling at 299,700 kilometers per second, 99.9% the speed of light. Your mass has increased due to relativistic effects. If you could somehow be weighed right now, you'd be many times heavier than you were when you started falling. Not because you've gained matter, but because kinetic energy has mass, and you're carrying an extraordinary amount of kinetic energy. 5 seconds. The mathematics of your position becomes strange. In normal space-time, you can describe your location with 3 spatial coordinates and 1 time coordinate. But near the event horizon, these coordinates start to swap roles. The radial direction, the direction pointing toward the singularity, begins to behave like a temporal dimension. Moving inward is no longer a choice about where to go. It becomes as inevitable as moving forward in time. You can no more stop your inward motion than you can stop tomorrow from arriving. 3 seconds. You're close enough now that if you could transmit a light signal outward, it would hover at the event horizon, frozen, never escaping, but never falling inward either. But you can't transmit anything. You're inside the region where even light aimed directly away from the singularity is pulled inward. Every direction you look, every direction you could point a flashlight, leads to the center. There is no out anymore. Out has ceased to exist as a concept. 2 seconds. The tidal forces are increasing again, even in this supermassive black hole where the event horizon itself is survivable. You're now deep enough that the gradient is becoming lethal. Your body, if it's still intact, is being pulled longer, thinner. The atoms in your feet are accelerating faster than the atoms in your head. The molecular bonds that hold your cells together are straining. 1 second. The event horizon is 300 kilometers away. You're so close to the speed of light that your mass has increased 100-fold. Your watch, if it's still running, is ticking at a normal pace from your perspective, but to anyone outside, time has nearly stopped. You're frozen in their reference frame, an image slowly fading into the infrared. But in your frame, the countdown continues. 0. You cross the event horizon, nothing happens. That's the most disturbing part. There's no barrier, no membrane, no sensation of transition. You don't feel the moment you pass from the outside universe into the interior of the black hole. There's no sign, no marker, no change in the texture of space-time. You simply continue falling, and the universe continues to exist around you. And the only difference is that now, mathematically, geometrically, physically, you cannot leave. The point of no return has passed, not in 5 hours, not in 5 minutes, not in 5 seconds, right now. And you didn't even notice. This is what happens at the event horizon. Absolutely nothing from your perspective. The drama is entirely external. To the outside universe, you've just vanished from causality. Every light ray you emit from this point forward is trapped inside the event horizon with you. Every radio signal, every gravitational wave, every possible form of information, all of it is severed from the rest of reality. As far as the universe is concerned, you've been erased, but from your perspective, you're still here, still falling, still conscious, at least for a little while longer. Let's talk about what you see. You look behind you toward what used to be out. The circle of compressed starlight is still there, still shrinking, but its behavior has changed. Before you crossed the event horizon, that light was being bent by gravity. Now it's being swept along with the curvature of space-time itself. The distinction is subtle, but fundamental. Outside the event horizon, light can orbit, can hover, can escape if aimed correctly. Inside, space-time itself is falling inward faster than light can climb out. The geometry of reality is collapsing toward the singularity, and you're riding that collapse. The circle of light behind you is getting smaller. Not because you're moving away from it, you are, but that's not why. It's shrinking because space-time is contracting. The universe you came from is being compressed into a smaller and smaller region of your past, and ahead of you, the darkness is infinite. You're now inside the black hole and the new countdown has begun. How long until you reach the singularity? For a supermassive black hole of 4 billion solar masses, the event horizon has a radius of roughly 12 billion kilometers. About 80 times the distance from the Earth to the Sun. The singularity is at the center. If you cross the event horizon at near light speed, the time remaining is no longer measured in hours, it's measured in seconds, maybe a few minutes, depending on your trajectory and the black hole's rotation. Let's say you have 5 minutes left, 300 seconds from the event horizon to the singularity. This is the final countdown, and unlike the previous 5 hours, this one is truly final. There is no theoretical escape, no mathematical loophole, no last-minute miracle. The singularity is in your future the same way next Tuesday is in your future. It's not a place you might go. It's a time you will reach. 4 minutes remaining. You're falling through the interior of the black hole, and the geometry here is unlike anything that exists in the outside universe. The radial direction, the direction toward the singularity, is now a time dimension. You're not traveling through space toward the center. You're traveling through time toward an event. The singularity isn't below you or ahead of you. It's in your future, and you're moving toward it at the rate of 1 second per second, the same way you've always moved toward tomorrow, 3.5 minutes. The tidal forces are intensifying. Even in a supermassive black hole, the closer you get to the singularity, the steeper the gravitational gradient. Your body, assuming it survived the crossing, is now under extreme stress. The difference in gravitational pull between your head and your feet is increasing exponentially. The atoms in your feet are being pulled with a force millions of times stronger than the atoms in your head. 3 minutes. Your body begins to disintegrate. Not from heat, not from radiation, but from tidal forces alone. The chemical bonds holding your molecules together are breaking, your cells rupture, your tissues separate. You're being reduced to your component atoms, and then those atoms are being pulled apart into subatomic particles. But here's the question that haunts physicists. Are you still conscious during this? Is there a moment, a final fraction of a second, where your brain is still processing information even as it's being torn apart? We don't know. The human brain has never been tested under conditions remotely like this. But if consciousness is an emergent property of neurons firing in patterns, and if those patterns can still exist even as the substrate is being destroyed, then maybe, you experience the final moments. 2.5 minutes. The circle of light behind you is now a pinpoint. The entire observable universe, every galaxy, every star, every planet that has ever existed, is compressed into a dot smaller than a grain of sand in your visual field, and it's fading. The photons from the outside universe are being redshifted into oblivion, stretched by the expanding space-time inside the black hole until their wavelengths become infinite. 2 minutes. You're no longer human. You're a stream of particles, a column of matter being funneled toward the singularity. If you could somehow look at yourself from the outside, which you can't, because light can't move sideways here, only inward, you'd see yourself stretched into a thread, millions of kilometers long and micrometers wide, a strand of what used to be a person. 1.5 minutes, the universe behind you disappears. The last photon from the outside world passes through your position, redshifted beyond detection, and then there's nothing. You're in absolute darkness now, not the darkness of a black void, but the darkness of a region where light itself has ceased to exist. You've outlived the photons. You've outlived causality. 1 minute. The tidal forces are now so extreme that individual atoms are being stretched. The electron clouds around nuclei are being distorted, pulled into elongated shapes. The fundamental forces that govern chemistry, the electromagnetic interactions between electrons and protons, are being overwhelmed by gravity. You're witnessing the breakdown of matter itself. 30 seconds. Your particles are approaching the singularity, and the geometry of space-time is becoming pathological. Curvature is approaching infinity. The equations of general relativity, Einstein's masterpiece, the theory that has accurately predicted everything from gravitational waves to the bending of light around stars, are beginning to produce nonsensical answers: division by zero, infinite density, infinite curvature. The math is screaming that it doesn't know what happens next. 20 seconds. Quantum effects are becoming important. At the scale of individual particles, at the extreme energies present near the singularity, quantum mechanics and general relativity are both trying to describe reality, and they're giving contradictory answers. This is the regime where we need a theory of quantum gravity, a unified framework that reconciles the quantum and the gravitational. We don't have that theory. We have candidates, speculations, mathematical frameworks like string theory and loop quantum gravity, but no confirmed, tested theory. So what happens in the next 20 seconds? Honestly, we don't know. 10 seconds. Here's what classical general relativity predicts. The singularity is a point of infinite density and zero volume. All the matter that has ever fallen into the black hole, every atom, every photon, every particle, is compressed into a geometric point with no size. The curvature of space-time at that point is infinite. time and space lose their meaning. The singularity is not a place in space. It's a moment in time, a boundary where the future ends, 5 seconds. But quantum mechanics suggests something different. At the Planck scale, 10 to the power of minus 35 meters, the smallest length that has physical meaning, space-time itself might become grainy, discrete, foamy. The smooth geometry of Einstein's relativity might break down into a quantum structure where space and time are no longer continuous. If that's true, then the singularity might not be a point of infinite density. It might be a quantum object, a Planck-scale structure where the matter is compressed to the absolute limit of physical reality, but not beyond. 3 seconds. Some theories suggest the singularity is a moment of bounce, that the collapsing matter reaches a maximum density and then rebounds, possibly creating a new universe on the other side. You wouldn't experience this as an explosion, because time inside the black hole is so distorted. You'd experience it as, what? Transition? Transformation? We genuinely don't know. 2 seconds. Other theories suggest the singularity is a firewall, a high-energy barrier at the event horizon, or deeper inside where quantum effects create a wall of radiation that incinerates anything approaching. This idea comes from attempts to reconcile black holes with the principles of quantum information theory. If it's true, you never reached this point. You were vaporized minutes ago, at the moment you crossed the horizon 1 second, and some theories suggest that black holes are gateways, wormholes to other regions of space-time or even other universes. If you could somehow survive the tidal forces, you'd emerge elsewhere, elsewhen, in a place where the laws of physics might be different, where the constants of nature have different values, where time runs backward or not at all. But these are speculations, mathematical possibilities. We have no observational evidence, no way to test these ideas, because information cannot escape a black hole. Whatever happens at the singularity stays at the singularity. 0. You reach the singularity, and the countdown ends. Not with an explosion, not with a flash of light, not with a sensation or a thought or a final moment of awareness. The timeline simply terminates. The future stops. Your world line, the path you've traced through space-time since the moment you were born, reaches its endpoint. From the perspective of the outside universe, this moment never arrives. You're still frozen at the event horizon, your image fading over billions of years as the photons carrying your light are stretched to infinite wavelength. The people who knew you will die. Their children will die. Their civilization will collapse. Stars will burn out. Galaxies will drift apart. The universe will expand into a cold, dark, empty void. And through all of that, you'll still be there, frozen at the edge of the black hole, asymptotically approaching, but never reaching the horizon. But in your reference frame, the journey is over. The countdown that began when you were 1,000,000 kilometers away, when you had 5.5 hours left, when escape was still theoretically possible, has reached 0. The clock has stopped. Not because time has stopped inside the black hole, your proper time continued ticking normally until the very end, but because you've reached a boundary where the concept of next moment has no meaning. Let's step back. Let's return to the outside universe and talk about what just happened from a different perspective. You started falling 5 hours and 5 minutes ago. For the first 5 hours, an outside observer with a powerful telescope could watch your descent. They'd see you accelerating, see the light from your body becoming red-shifted as you fell deeper into the gravitational well. They'd see you approaching the event horizon, getting closer and closer, your image slowing down as time dilation became extreme. And then, at the 5-hour mark, something strange would happen. Your image would freeze. Not suddenly, there'd be no moment where motion stops. But gradually, asymptotically, your movement would slow until it became imperceptible. The light from your body would shift from red to deep red to infrared to microwave to radio wave, the wavelength stretching as the photons climbed out of the deepening gravitational well. After a few more minutes, you'd fade from view entirely. Not because you've disappeared, but because the photons carrying your image are so red-shifted that no detector can capture them. You've become a ghost, an afterimage, a memory slowly dissolving into the cosmic background radiation. From the perspective of the outside universe, you never cross the event horizon. You never reach the singularity. You never experience those final 5 minutes. You're stuck at the threshold forever, frozen in time, a permanent fixture of the black hole's edge. But this isn't a paradox. Both perspectives are true. From your frame, you crossed the horizon and reached the singularity. From the outside frame, you never crossed and never will. This is the nature of relativity. There is no universal now, no objective timeline that everyone agrees on. Time is local. Your 5 minutes inside the event horizon are real, even though they never happen from an external viewpoint. This is what makes black holes so philosophically disturbing. They create a divergence in causality. Two observers, you and someone watching from a safe distance, experience mutually contradictory timelines, and both are correct. You die at the singularity. You never die at the singularity. Both statements are true. Now, let's ask a darker question. What if you weren't alone? What if you weren't alone? Imagine a second person falling into the black hole alongside you, maybe a fellow astronaut from the same failed mission, maybe someone who jumped in trying to save you. It doesn't matter. What matters is that they're falling too, but they started their fall from a slightly different position. Let's say they were 100 kilometers behind you when the descent began. You're both falling toward the same black hole. You're both experiencing the same physics. But you're not experiencing the same timeline. During the first few hours of the fall, you could still communicate. Radio signals traveling at the speed of light would cover the 100 kilometers between you in a third of a millisecond. You could talk in real time, share observations, coordinate your instruments. You'd both see the same accretion disk, the same distorted star field, the same approaching darkness. But as you got closer to the event horizon, something would change. The signals from your companion, the radio waves carrying their voice, the light reflecting off their spacesuit, would begin to arrive at longer and longer intervals. Not because the distance between you was increasing, but because time dilation was affecting each of you differently. You're closer to the black hole, so you're deeper in the gravitational well, so time runs slower for you than for them. From your perspective, their clock is running fast. From their perspective, your clock is running slow. The same effect that would make you appear frozen to a distant observer makes your companion appear accelerated to you. By the time you cross the event horizon, the time gap has become extreme. To you, only 5 hours have passed since you started falling. But for your companion, 100 kilometers farther from the black hole, maybe 6 hours have passed, or 10 hours, or 100, depending on the exact geometry. They've aged faster than you. They've experienced more subjective time. And here's the cruel part. From their perspective, watching you fall ahead of them, You never cross the event horizon. You slow down, freeze, fade. They watch you die in ultra-slow motion, your image stretched and distorted until you disappear into the redshift. But from your perspective, you crossed the horizon hours ago. You're already inside, already approaching the singularity, while in their timeline, you're still at the threshold. Now imagine they try to follow you. They accelerate, trying to catch up, trying to reach you before you hit the singularity. But they can't. The geometry won't allow it. By the time they cross the event horizon, from their perspective, you've already been falling inside for an eternity. The singularity has already claimed you. They could chase you forever and never catch up, because the interior of a black hole is structured in such a way that later observers can never reach earlier ones. This is one of the most disturbing features of black hole physics. If you fall into a black hole and someone jumps in after you to save you, they will always arrive too late. Not because they were slow, not because they hesitated, but because the geometry of space-time inside the event horizon makes catching up physically impossible. Your future singularity and their future singularity are separate points in space-time, and no amount of acceleration can merge them. So you die alone. Even if 1,000 people jumped in after you, even if they all crossed the horizon within seconds of each other from an external viewpoint, each of you would experience the interior in isolation, separated by the inexorable structure of time inside the black hole. But let's imagine something different. Let's say you're not falling alone, and you're not falling behind someone. Let's say you're falling alongside someone, a companion who entered the gravitational well at the exact same distance, at the exact same time, with the exact same velocity. You're synchronized, twin astronauts in twin spacecraft, descending in parallel. For the first few hours, you'd experience the fall identically. Same velocity, same time dilation, same tidal forces. You could look across the void between your ships and see each other, watch each other's faces, share the terror and wonder of the descent. But as you approach the event horizon, something strange would happen. The tidal forces, the same forces stretching you head to foot, would also be squeezing you side to side. This is a consequence of the geometry of curved space-time. Gravity doesn't just pull things together along the radial direction, it also compresses them along the tangential directions. It's called the squeeze effect, and it's a prediction of Einstein's equations. So even though you started falling in parallel, you and your companion would begin to drift closer together. Not because you're steering toward each other, but because space-time itself is contracting in the transverse directions. The distance between your ships would shrink. Slowly at first, then faster as you approached the horizon. By the time you crossed the event horizon, you might be only meters apart. Inside the black hole, the compression would continue. You'd drift closer, closer, until eventually your ships collided, not from any horizontal motion, but from the geometric contraction of space itself. This is the fate of all matter falling into a black hole. It doesn't just fall inward, it's funneled inward, compressed into a narrowing cone, all trajectories converging on the singularity. If you could watch 1,000 objects fall into a black hole from different angles, you'd see them all gradually spiraling together, their paths merging, until they arrived at the singularity as a single compressed stream. Now, let's change the scenario again. Let's talk about what happens if you fall into a rotating black hole. So far, we've assumed the black hole is non-rotating, what physicists call a Schwarzschild black hole, the simplest possible solution to Einstein's equations. But in reality, almost all black holes rotate. They form from collapsing stars or merging stellar remnants, and those objects carry angular momentum. When they collapse, the rotation speeds up, the same way a figure skater spins faster when they pull their arms in. By the time the black hole forms, it's spinning at a significant fraction of the speed of light. A rotating black hole, a Kerr black hole, has a very different interior structure than a non-rotating one. It has two event horizons instead of one, an outer horizon and an inner horizon. And between them, there's a region called the ergosphere, where space-time itself is being dragged around the black hole at relativistic speeds. If you fall into a rotating black hole, your timeline becomes even more complicated. Let's say you're falling into a black hole that's rotating at 90% of the maximum possible rate. This is common for black holes formed from merging binary systems. You start your descent from the same 1 million kilometers out, same 5-hour approach time. But as you get closer, you notice something different. You're not falling straight inward. You're being dragged sideways, pulled into a spiral trajectory that circles the black hole even as it descends. This is frame dragging, the effect Einstein's equations predict near any rotating, massive object. Near Earth, frame dragging is minuscule. Satellites in orbit experience a tiny sideways drift, measurable only with extremely precise instruments. But near a rotating black hole, frame dragging is extreme. Space-time itself is rotating, and you're embedded in that rotation, whether you want to be or not. By the time you're 1 hour from the outer event horizon, you're no longer falling straight down. You're spiraling, circling the black hole once every few minutes, descending in a corkscrew pattern. The accretion disk is whipping past you in a blur. The stars behind you are streaking into arcs of light. You're in a gravitational vortex, and there's no way to swim against the current. When you cross the outer event horizon of a rotating black hole, you enter the ergosphere. This is a region where you can still, theoretically, escape, but only if you have enough energy. The catch is that within the ergosphere, you cannot remain stationary. You must orbit the black hole. Space-time is rotating so fast that staying still would require moving faster than light, which is impossible. So you're forced to circle, dragged along by the rotating geometry, even if you fire your engines in the opposite direction. This is where the timeline gets strange. Inside the ergosphere, time and space mix in unusual ways. Some trajectories inside the ergosphere can actually escape back to the outside universe, but only if they shed energy in the process. This is the basis of the Penrose process, a theoretical method for extracting energy from a rotating black hole. An object falls into the ergosphere, splits into two pieces, and one piece falls inward while the other escapes outward with more energy than the original object had. But you're not trying to extract energy, you're just falling. So you cross the ergosphere, spiral deeper, and approach the inner event horizon. The inner horizon is where things get truly strange. According to the mathematics of Kerr black holes, the inner horizon is unstable. Any small perturbation, a single photon, a fluctuation in the quantum vacuum, gets amplified to infinite energy as it approaches the inner horizon. This is called the mass inflation instability, and it suggests that the inner horizon is not a smooth boundary, but a violent, high-energy region where space-time itself becomes unstable. Some physicists think this instability means the inner horizon doesn't really exist in physical black holes. The mathematics predicts it, but the real universe might smooth it out, replace it with a chaotic transition zone where quantum effects dominate. Others think the inner horizon is real but lethal, a firewall of radiation that incinerates anything trying to cross it. If you somehow survive crossing the inner horizon, and this is a big if, you'd enter the innermost region of the black hole, where the singularity awaits. But in a rotating black hole, the singularity isn't a point, it's a ring. The Kerr solution predicts that the singularity of a rotating black hole is a one-dimensional ring, like the edge of a spinning disk, located at the equator of the black hole's rotation. If you approached it from the poles, you might be able to pass through the ring without hitting it, and on the other side, what? The mathematics suggests that passing through the ring's singularity might lead to another region of space-time, not another part of our universe, but a different space-time entirely, possibly with different physical laws, different constants of nature, different dimensionality. Some solutions even suggest closed time-like curves, paths through space-time that loop back on themselves, allowing time travel to the past. But these are speculative solutions to the equations, not predictions we can test. The reality is that we don't know what happens near the ring singularity. Quantum effects that aren't included in classical general relativity almost certainly become important. The structure might collapse, it might stabilize, it might do something we haven't even imagined. What we do know is that your timeline, the countdown from the moment you started falling, leads to this ring. And whether you're annihilated at the inner horizon, vaporized at the ring itself, or somehow pass through to another region of space-time, the journey ends here. The clock stops. The countdown reaches 0. Let's pull back again and ask a different kind of question. How does the size of the black hole affect your timeline? We've been assuming a supermassive black hole, the kind that makes crossing the event horizon survivable. But what if you fell into a stellar mass black hole, the kind formed from a single collapsing star? A stellar mass black hole with 10 times the mass of the Sun has an event horizon radius of about 30 kilometers. Compare that to the 12 billion kilometer radius of the supermassive black hole we've been discussing. The difference is almost 500,000 times. And because tidal forces scale inversely with the square of the radius, the tidal forces at the event horizon of the stellar mass black hole are trillions of times stronger. If you fell toward a stellar mass black hole from 1 million kilometers out, you wouldn't survive anywhere near the event horizon. You'd be ripped apart by tidal forces while you were still thousands of kilometers away. The exact distance depends on your orientation and the tensile strength of your tissues, but a reasonable estimate is that spaghettification becomes lethal at around 1,000 kilometers from the horizon. So your 5-hour countdown would be cut short. At the 4-hour mark, when you were still 200,000 kilometers from the event horizon, you'd start to feel the tidal forces. At 4 hours and 30 minutes, they'd be painful. At 4 hours and 50 minutes, they'd be unbearable. And at 4 hours and 59 minutes, your body would begin to tear apart. Your actual timeline would be 5 hours from the safe zone to the spaghettification radius, then maybe 1 more minute of excruciating disassembly, and then nothing. You'd be a cloud of atoms still falling inward, still approaching the event horizon, but no longer conscious, no longer experiencing anything. The remaining few seconds of free fall to the horizon would happen to your component particles, not to you. So the answer to how long would it take to fall into a black hole depends critically on which black hole. For a stellar mass black hole, 5 hours until death, 5 hours and a few minutes until your remains cross the horizon. For a supermassive black hole, 5 hours until the horizon, then a few more minutes until the singularity, with death somewhere in between depending on how deep the tidal forces become lethal. Now let's ask an even stranger question. What if the black hole is evaporating? Stephen Hawking discovered in 1974 that black holes aren't entirely black. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. Virtual particle pairs pop into existence just outside the horizon, and occasionally one particle falls in while the other escapes. The escaping particle carries energy away from the black hole, causing it to slowly lose mass and shrink over time. For a stellar mass black hole, the time scale for evaporation is enormous, around 10 to the power of 67 years, far longer than the current age of the universe. So if you're falling into a stellar mass black hole, evaporation is irrelevant. The black hole will outlive you, your species, your planet, your star, and your galaxy. But for a small black hole, a primordial black hole formed in the early universe with a mass of, say, 1 billion kilograms, about the mass of a large asteroid, the evaporation timescale is much shorter. A black hole of this mass would have a lifetime of around 10 billion years, roughly the current age of the universe. If you happened to fall toward one of these small black holes late in its life, you might witness the final stages of evaporation. And those final stages are dramatic. As a black hole loses mass, it shrinks, and as it shrinks, the Hawking radiation gets hotter and more intense. In the last second of a black hole's life, it releases as much energy as a nuclear bomb. In the last microsecond, it releases as much energy as a star. And in the final Planck time, the last 10 to the power of minus 43 seconds, it releases an enormous burst of high-energy radiation and possibly exotic particles. If you were falling toward a small black hole in the final moments of its evaporation, your timeline would end not at the singularity, but in the fireball of the black hole's death. You'd be vaporized by Hawking radiation before you ever crossed the event horizon. The countdown would terminate in a flash of gamma rays, but for any black hole larger than a few billion kilograms, evaporation is slow enough that you'd fall in and reach the singularity long before the black hole evaporates. The countdown proceeds as described. Let's ask one more question before we move to the final phase. What happens if you try to resist? So far, we've assumed you're in free fall, no engines, no thrust, just gravity pulling you down. But what if you had a spacecraft with a powerful engine? What if you fired your thrusters at full power, trying to slow your descent or even escape? The answer depends on where you are in the timeline. In the first hour, when you're still far from the event horizon and falling at only a fraction of the speed of light, a sufficiently powerful engine could slow you down. You couldn't escape. Remember, escape velocity at 1 million kilometers is 40% the speed of light, and no rocket humanity could build reaches that speed. But you could slow your descent, stretch out the timeline, delay the inevitable. If you fired a thruster producing one Earth gravity of acceleration in the direction opposite your fall, you'd slow from 50 kilometers per second to 0 over the course of, well, you'd need to do the math, but it's on the order of hours. You could buy yourself time, not forever, but time. However, this comes at a cost. Resisting gravity means you're no longer in free fall, which means you'd feel acceleration. One gravity of acceleration doesn't sound like much, it's what you feel standing on Earth, but sustaining it for hours while also experiencing the tidal forces of the black hole would be agonizing. Your body would be under constant stress, and you'd be burning fuel at an enormous rate. Eventually, your fuel would run out, the thrusters would cut off, and you'd resume falling, now from a lower altitude, with less time remaining. In the second hour, as you got closer to the event horizon, the amount of thrust needed to resist gravity would increase exponentially. By the time you were 10,000 kilometers from the horizon, you'd need to accelerate at hundreds of gravities just to maintain your position. The engine would crush you against the back of the spacecraft, your bones would shatter, your organs would fail. And by the time you were within a few hundred kilometers of the event horizon, no amount of thrust would be enough. The required acceleration would exceed the speed of light, which is impossible. At that point, resistance becomes physically meaningless. You could fire the most powerful engine imaginable, and you'd still be falling inward, because space-time itself is falling inward faster than you can climb out. This is the essence of the event horizon. It's the boundary where escape becomes impossible. Not just practically difficult, but physically, geometrically, fundamentally impossible. Beyond that boundary, even light pointed directly outward is dragged inward. Your thruster could produce infinite thrust and you'd still fall. So, if you try to resist, the only thing you accomplish is postponing the inevitable and making the journey more painful. The countdown continues, the clock keeps ticking, the singularity waits. Let's talk about what other people see while you fall. You have a companion, let's call them Alex, who's watching from a safe distance. They're in a spacecraft hovering far from the black hole, positioned at a stable orbit where they can observe without falling in themselves. They have a powerful telescope trained on you, tracking your descent in real time, or what they think is real time. From Alex's perspective, your fall looks very different than it feels to you. For the first hour, they watch you accelerate smoothly inward. Your spacecraft is a bright dot against the darkness, illuminated by the glowing accretion disk behind you. They can see you clearly, track your position, measure your velocity. You're falling at 50 kilometers per second, then 100, then 150. Everything proceeds exactly as the physics predicts. But as you approach the 2-hour mark, Alex starts to notice something strange. Your image is getting dimmer. Not because you're farther away, you're actually getting closer to the black hole, which means closer to the region Alex is observing. But the light from your spacecraft is redshifting. The photons climbing out of the deepening gravitational well are losing energy, their wavelengths stretching toward the red end of the spectrum. At 2.5 hours, your spacecraft has shifted from white to orange. At 3 hours, it's deep red. At 3.5 hours, it's infrared, invisible to the naked eye, but still detectable with Alex's instruments, and your motion is slowing. Not your actual motion from your perspective, you're still accelerating, still falling faster and faster, but the rate at which Alex sees you moving is decreasing. This is time dilation. The closer you get to the event horizon, the slower your clock runs relative to Alex's clock. They watch your descent in slow motion, getting slower and slower as you approach the point of no return. At 4 hours from Alex's perspective, you're visibly crawling. Each second of their time corresponds to a fraction of a second of your time. They watch you inch toward the event horizon at an ever-decreasing rate. At 4.5 hours, you're nearly frozen. Your position is barely changing. The light from your spacecraft is now deep in the infrared, almost undetectable. And at 5 hours, the moment when, from your perspective, you cross the event horizon, Alex sees nothing. No sudden change, no disappearance, just a continued slowing, a continued fading, until you're so redshifted and so time dilated that you're effectively frozen at the threshold. From Alex's perspective, you never cross the event horizon. Not in 5 hours, not in 5 years, not in 5 billion years. You're stuck there, asymptotically approaching but never reaching the boundary, your image fading into the cosmic background, radiation over the course of eons. This is one of the strangest predictions of general relativity. The crossing of the event horizon is an event that happens in your reference frame, but never happens in Alex's reference frame. Both perspectives are equally valid. You cross the horizon and die at the singularity. You never cross the horizon and remain frozen at the edge forever. There's no contradiction because there's no universal now that both of you share. But let's say Alex refuses to accept this. They want to know what happened to you. They want to see you cross the horizon, see you reach the singularity. So they decide to fall in after you. Alex fires their engines and begins their own descent. They're starting from the same 1 million kilometer distance you started from, but they're beginning 4 hours after you did. They fall along the same trajectory, experiencing the same acceleration, the same tidal forces, the same time dilation. From Alex's perspective, what do they see? At first, they still see you frozen near the event horizon, fading and red-shifted. But as Alex accelerates inward as they fall deeper into the gravitational well, their reference frame begins to match yours. The time dilation difference between you and Alex decreases, and as it does, your frozen image starts to move again. Alex watches you unfreeze. Your spacecraft starts descending again, slowly at first, then faster. The redshift decreases. You're no longer frozen at the edge, you're falling. And from Alex's new perspective, you're falling quickly. By the time Alex is 3 hours into their own descent, they see you cross the event horizon. Not frozen, not fading, but actually crossing. Because now Alex is in a reference frame where the event horizon is approachable, where crossing it is a physical event rather than an asymptotic limit. But here's the tragedy. Alex can see you cross the horizon, but they can never catch up to you. Even though you're both falling inward, even though you're both moving at relativistic speeds, the structure of space-time inside the event horizon prevents Alex from reaching your position. You're ahead of them in time, falling toward an earlier singularity moment, and no amount of acceleration can close that gap. Alex watches you fall deeper inside the black hole. They watch you stretch, distort, fragment. They watch you reach the singularity and disappear. And then, minutes or hours later, depending on the exact timing, Alex reaches their own singularity. Separate from yours, causally disconnected. Two people fell into the same black hole. Both died at the singularity, but they died at different singularities, separated by the strange geometry of the black hole's interior. Now let's ask a different question. What if you fell into a black hole that was actively feeding? Most black holes in the universe aren't isolated objects floating in empty space. They're surrounded by accretion disks, swirling masses of gas, dust, and plasma that are gradually spiraling inward. This matter heats up due to friction and compression, reaching temperatures of millions of degrees and emitting enormous amounts of radiation across the electromagnetic spectrum. If you're falling into an active black hole, one with a thick, bright accretion disk, your experience changes dramatically. First, the radiation. At a distance of 1 million kilometers, you're already inside the region where the accretion disk's radiation is significant. X-rays, ultraviolet light, gamma rays, all of it is streaming outward from the superheated matter near the event horizon. If you're unshielded, this radiation will kill you long before the tidal forces do. It would take minutes to hours depending on the intensity, but the result is the same. Radiation poisoning, cellular breakdown, death. Let's assume you have shielding. Your spacecraft has thick layers of lead and water to absorb the radiation. You're protected, at least for a while. As you fall deeper, the radiation intensity increases. At 500,000 kilometers, it's 10 times stronger. At 100,000 kilometers, it's 100 times stronger. Your shielding is heating up, glowing red hot from the absorbed energy. The interior of your spacecraft is becoming an oven. At 10,000 kilometers from the event horizon, the radiation is so intense that your shielding begins to fail. The lead is vaporizing. The water is boiling away. And even if the shielding held, the heat transfer alone would cook you alive. But there's another hazard, the accretion disk itself. As you fall inward, you're not falling through empty space. You're falling through the outer regions of the disk, a tenuous but still substantial amount of matter. At first, it's like falling through a faint mist. You barely notice it. But as you get closer to the event horizon, the density increases. At 1,000 kilometers from the horizon, you're plowing through gas at a density comparable to Earth's upper atmosphere. The friction is generating heat. Your spacecraft is now a meteor burning up as it falls. The outer hull is ablating, shedding layers of molten metal. The interior temperature is climbing past the boiling point of water, past the melting point of aluminum, past the limits of human survival. You're being cremated as you fall. And if you somehow survive the heat, maybe you're in some indestructible capsule, some hypothetical material that can withstand millions of degrees, you still have to contend with the impacts. The accretion disk isn't uniform. It has clumps, streams, eddies of denser material. As you fall through it at a significant fraction of the speed of light, even a tiny particle becomes a relativistic projectile. A dust grain massing 1 milligram, hitting you at 50% the speed of light, carries the kinetic energy of several tons of TNT. It would punch through your spacecraft like a bullet through the tissue paper. And there are millions of such particles in your path. So, if you're falling into an actively feeding black hole, your timeline is much shorter. You might not even make it to the event horizon. You'd be incinerated, shredded, and vaporized by the environment around the black hole long before the black hole itself killed you. This is what makes supermassive black holes at the centers of quasars so lethal. They're not dangerous because of tidal forces. Those are relatively gentle at their enormous event horizons. They're dangerous because of the accretion disks. The radiation alone from a quasar's accretion disk would be lethal at distances of light years. You wouldn't need to fall in. You'd die just from being in the same region of the galaxy. But let's assume you're falling into a quiescent black hole, one with no accretion disk, no radiation, no debris, just the black hole itself and empty space. This is the cleanest scenario, the one where the timeline we've been describing actually applies. Now let's ask, what if you're not falling into the black hole voluntarily? What if you're in orbit around it and something goes wrong? Orbits around black holes are stable, just like orbits around stars or planets, as long as you're outside a critical radius called the innermost stable circular orbit, or ISCO. For a non-rotating black hole, the ISCO is at 3 times the radius of the event horizon. For a maximally rotating black hole, it's at about half the event horizon radius, just outside the horizon itself. If you're orbiting outside the ISCO, your orbit can last forever. You're safe, at least from falling in. But if you're orbiting at the ISCO or inside it, your orbit is unstable. The slightest perturbation, a tiny thruster misfire, a small gravitational tug from a passing object, will cause your orbit to decay. And once it starts decaying, it doesn't stop. Let's say you're in a circular orbit at the ISCO of a supermassive black hole. You're traveling at about 50% the speed of light, circling the black hole once every few hours. It's a stable orbit, but just barely. And then something happens. Maybe a micrometeorite hits your spacecraft, maybe a thruster fires accidentally, maybe the black hole's rotation shifts slightly due to a recent accretion event. Whatever the cause, your orbit shifts. You're now on a trajectory that's not quite circular. It's elliptical, with the low point of the ellipse dipping just inside the ISCO. On the first orbit, nothing seems wrong. You complete the circle and return to your starting point. But on the second orbit, you notice your altitude has dropped slightly. The low point of your ellipse is now deeper inside the ISCO, and the orbital period has shortened. You're circling faster. This is orbital decay. Each orbit takes you deeper. Each orbit shortens the period. And the process accelerates. The deeper you go, the stronger the gravitational pull, the faster the decay. After 10 orbits, you're noticeably lower. After 100 orbits, you're in a rapidly descending spiral. And after 1,000 orbits, depending on the exact parameters, you're close enough to the event horizon that the decay becomes catastrophic. Your orbital period drops from hours to minutes to seconds. In the final minute, you complete dozens of orbits, spiraling inward like water down a drain. The accretion disk, if there is one, becomes a blur. The stars outside are streaking into continuous rings of light. You're spinning so fast that centrifugal forces are pinning you against the wall of your spacecraft, with dozens of gravities of acceleration. And then, on the final orbit, you cross the event horizon, not falling straight down, but spiraling in at an angle, still carrying your orbital angular momentum. You're not just falling inward, you're spinning inward, tracing a helical path toward the singularity. From an outside observer's perspective, they'd watch your orbit decay over days or weeks or months, depending on how close you started to the ISCO. They'd see you spiraling faster and faster, the time between each orbit shrinking, until you disappeared into the redshift at the event horizon. From your perspective, the timeline is different. Each orbit feels normal. You don't perceive the decay on short time scales. But over the course of hours or days, you'd notice the changes. Your instruments would show the altitude dropping, the orbital period shortening, the tidal forces increasing. You'd know what was coming. You'd have time to prepare, to send final messages, to make peace with the inevitable. And then, in the final minutes, the spiral would tighten so quickly that you wouldn't have time to think. You'd just spin, faster and faster, until the event horizon swallowed you. This is how most matter actually falls into black holes in the real universe, not in straight radial infall, but in spiraling decay from destabilized orbits, stars torn apart by tidal forces, gas clouds disrupted by gravitational shear, entire solar systems drifting too close and being pulled into the vortex. Every particle that crosses the event horizon carries a history of spiraling inward, orbiting dozens or thousands of times before the final plunge. And each one experiences the same countdown, the gradual decay, the accelerating spiral, the final chaotic moments before crossing the threshold. Now, let's shift perspective one more time. Let's talk about what happens if you're not the one falling, but you're the one watching someone else fall, and that person is someone you care about. Imagine you're in a spacecraft at a safe distance, orbiting the black hole in a stable configuration. Your partner, let's call them Sam, is in another spacecraft that's fallen into a decaying orbit. You watch them spiral inward, unable to help. Your ship doesn't have enough fuel to reach them. Even if it did, you couldn't match their trajectory without falling in yourself. For the first few hours, you can still communicate. Sam's voice comes through the radio clearly. You talk about ordinary things, memories, regrets, things left unsaid. Sam describes what they're seeing, the distorted star field, the glowing accretion disk, the encroaching darkness. But as Sam gets closer to the event horizon, the radio transmissions start to change. Sam's voice gets deeper. The pitch drops, octave by octave, as the radio waves are red-shifted by the gravitational well. Words that Sam speaks in normal speed reach you slowed down, stretched out. A sentence that takes Sam 3 seconds to say takes you 5 seconds to hear, then 10 seconds, then 30. And the time gap between your transmissions and Sam's responses gets longer. You say, "I love you," and Sam says, "I love you too." But by the time you hear their response, a minute has passed, then 5 minutes, then an hour. In the final stages, as Sam approaches the event horizon, the time dilation becomes extreme. You watch Sam's spacecraft slow to a crawl. You hear Sam's voice drop to a deep, slow rumble, each word taking minutes to complete, and the light from Sam's ship fades, shifting from white to red to infrared. The last thing you hear is Sam saying your name. It takes 10 minutes for Sam to finish saying it, the syllables stretched into a long, distorted groan. And then silence. The radio goes dead. Not because the transmission stopped, but because the wavelength has stretched so long that it's no longer detectable as a radio wave. It's become a low-frequency electromagnetic wave with a wavelength measured in kilometers, undetectable by your equipment. Sam's spacecraft is still visible barely, a dim red point hovering at the edge of the event horizon. Over the next hours it fades. Over the next days it becomes invisible. And over the next years, if you stayed to watch, it would remain frozen there, an afterimage slowly dissolving into the void. But Sam, from Sam's perspective, crossed the event horizon hours ago. Sam is already gone, already at the singularity, already dead. And you'll spend the rest of your life knowing that the last image you have of Sam, frozen at the edge of the black hole, is a lie, a ghost, a relic of photons that escaped just before the point of no return. This is the emotional weight of black hole physics. It's not just about the person falling in, it's about everyone watching, everyone left behind, everyone who has to live with the fact that their loved one is both gone and still there, both dead and frozen in time, both lost and visible. The countdown doesn't just affect the person falling, it affects everyone who cares about them. Let's return to you. You've crossed the event horizon, the countdown that began 5 hours ago when you were 1,000,000 kilometers away has entered its final phase. You're inside the black hole now, falling toward the singularity, and the clock is ticking down in minutes rather than hours. But before we talk about those final minutes, let's address a question that's been lurking beneath the surface of this entire discussion. Is any of this actually survivable? The answer is complicated. From a purely physical standpoint, if you're falling into a supermassive black hole, one of the truly enormous ones at the centers of giant galaxies, the tidal forces at the event horizon are gentle. The gradient of gravity across your body would be less than what you experience standing on Earth. You could cross the threshold intact, conscious, and alive. But consciousness is fragile. The human brain requires a steady supply of oxygenated blood, maintained temperature, and protection from radiation. Inside a black hole, all of these become problematic. If you're in a spacecraft with life support, you might survive for a while. Your oxygen supply would last as long as the tanks hold out, maybe hours, maybe days if you're conserved. Your heating or cooling systems would function until the power runs out. You'd have time. Not unlimited time, but time to experience the interior of the black hole as a conscious observer. If you're in just a spacesuit, your timeline is shorter. Most suits carry oxygen for 6 to 8 hours. You crossed the event horizon 5 hours into your fall, so you'd have 1 to 3 hours of breathable air left. Enough to reach the singularity, assuming the black hole is large enough that the trip from horizon to center takes less than a few hours. But if you're unprotected, if your spacecraft failed and you're exposed to vacuum, you'd lose consciousness in about 15 seconds. Your blood wouldn't boil like in the movies. The blood vessels would keep the pressure contained. But the lack of oxygen to your brain would shut you down quickly. You'd die within 2 minutes, long before you crossed the event horizon. So, the question, how long does it take to fall into a black hole, has a different answer depending on whether we're measuring your journey or your consciousness. Your body might take 5 hours and 15 minutes to travel from the safe zone to the singularity. But your awareness might only last 5 hours and 30 seconds if you're in vacuum, or 5 hours and 3 days if you're in a well-supplied spacecraft. Let's assume the best case. You're in a spacecraft. You have life support, you have power, and you're conscious as you cross the event horizon. What do you experience in those final minutes? The first thing you notice is that the universe behind you has vanished. Not faded, vanished. The circle of compressed starlight that was shrinking throughout your fall has finally winked out. The last photons from the outside universe have passed through your position, and no new ones are coming. You're in absolute darkness now. Your instruments show nothing. Any camera pointed outward captures only black. Any radio receiver tuned to any frequency hears only silence. You're cut off from the universe in the most complete way possible. No light, no radiation, no information of any kind can reach you from outside. But if you point a light inward, toward the singularity, you can see something. Your flashlight's beam extends ahead of you, illuminating what? There's no matter here. The interior of a black hole in the simplest models is empty space, vacuum, just you, and the curved geometry. But the beam doesn't travel straight. It curves, bends, warps according to the extreme curvature of space-time this close to the singularity. You might see the light curve back toward you, creating strange loops and patterns, or it might simply disappear into the darkness ahead, swallowed by the approaching singularity. You check your clock. Let's say you have 5 minutes remaining until you reach the singularity. 5 minutes of existence left. What do? Some people might pray, some might review their lives, thinking about the moments that mattered, the people they loved, the choices they made. Some might rage against the dying of the light, firing their thrusters uselessly against the inward pull of space-time. But some might do something different. Some might take measurements. You're experiencing something no human has ever experienced. You're inside a black hole, the most extreme environment the universe can create. Every second you remain conscious, every data point you record is unprecedented. You can't transmit this information back to the outside universe. The event horizon prevents that. But you can record it. You can write it down. You can make observations, take notes, capture as much data as possible in the time you have left. Why? Because even though the information can't escape, even though no one will ever read your notes or see your data, the act of recording it matters. It's defiance. It's the assertion that even here, at the edge of oblivion, consciousness matters. Observation matters. Understanding matters. You point your instruments at the geometry around you. You measure the curvature of space-time, you calculate the tidal forces, you document the behavior of light near the singularity, and you write down what you see. 4 minutes remaining. The tidal forces are increasing now. Even in this supermassive black hole, the closer you get to the singularity, the steeper the gradient. Your body is beginning to feel the stretch. It's subtle. Nothing like the violent spaghettification you'd experience in a smaller black hole, but it's there. A tightness in your spine, a pulling sensation in your legs. Your body is being gently elongated by the differential gravity. You try to take a deep breath, but it's harder than it should be. Your chest feels compressed. This is the squeeze effect, the transverse component of the tidal force pressing in from the sides even as it pulls along the length. Your body is being shaped by gravity into a long, thin column. 3 minutes remaining. You're wondering if there's any hope, any possibility, however remote, that you might survive this. And you remember the theories, the speculations, the mathematical solutions that suggest black holes might not be dead ends but passages. What if the singularity isn't a point of destruction but a transition? What if, in the final moment, your consciousness doesn't end but transforms? Some theories in quantum gravity suggest that the singularity might be a quantum bounce, a moment where the collapsing matter reaches maximum density and then rebounds, possibly creating a new region of space-time on the other side. If that's true, then you're not falling toward an ending, you're falling toward a beginning. The singularity would be a threshold, and crossing it would be like being born into a new universe with different laws, different constants, different possibilities. But you don't know. No one knows. The mathematics breaks down at the singularity, and quantum effects that aren't included in Einstein's equations become important. You're about to find out what happens when theory meets reality, when speculation meets experiment. You're the experiment. 2 minutes remaining. Your spacecraft is groaning. The structural supports are flexing under the tidal stress. Rivets are popping, panels are buckling. The ship was designed for the vacuum of space and the acceleration of rocket engines, not for the tidal forces of a black hole's interior. It's coming apart. You hear a hiss. Air is leaking. The hull has ruptured somewhere, a small tear that's venting your atmosphere into the void. You have maybe 60 seconds before the pressure drops too low to breathe. You seal your helmet. Your suit has its own air supply, 30 minutes worth, more than enough for the time you have left. 1.5 minutes remaining. The tidal forces are no longer subtle. Your spine is bending. Your legs are being pulled away from your torso with increasing force. You curl into a ball, trying to minimize the distance between your extremities, trying to reduce the tidal gradient across your body. It helps, but only slightly. The pain is extraordinary. It feels like you're being stretched on a rack, every joint being slowly pulled apart. Your bones are creaking, your muscles are tearing, and yet you're still alive, still conscious, still recording data. 1 minute remaining. Your spacecraft disintegrates. The hull tears apart completely, and the pieces along with you continue falling inward separately. You're in free space now, tumbling through the interior of the black hole in your spacesuit, surrounded by debris from your ship. You watch the pieces drift apart, pulled by the tidal forces into separate trajectories. Some are ahead of you, falling faster. Some are behind. Some are to the side, being squeezed inward by the transverse tidal forces. The cloud of debris is spreading out along the radial direction and compressing along the tangential directions, forming a long, thin stream of matter, all falling toward the same point. 30 seconds remaining. You can see the singularity now. Not visually. There's no light, nothing to see, but you can feel it. You can sense it the way you might sense a cliff edge in the dark, a presence in the space ahead of you. It's not a place. It's not a thing. It's a moment in time that's approaching, a future event that you cannot avoid. The geometry around you is becoming pathological. Straight lines curve back on themselves. Time and space have traded roles completely. The direction you're falling isn't down anymore. It's forward in time. The singularity isn't below you. It's in your future, and you're moving toward it at exactly 1 second per second, the same rate you've always moved toward the future. 20 seconds remaining. Your body is failing. The tidal forces are stronger than the tensile strength of human tissue. Your skin is stretching. Your organs are shifting. Blood is pooling in your extremities, creating pressure differentials that your cardiovascular system wasn't designed to handle. But your brain is still functioning. The neurons are still firing. You're still conscious, still experiencing, still observing. The human brain is remarkably resilient, even as your body is being destroyed. The electrical patterns that constitute your thoughts, your memories, your sense of self, those patterns persist. 10 seconds remaining. You try to send one final transmission. You know it won't reach the outside universe. The event horizon prevents that, but you send it anyway. A message to no one, a declaration to the void. I'm here, you say. I crossed the threshold. I experienced the interior of a black hole. I made it this far, and in 10 seconds, I'll know what's at the center. I'll know what happens at the singularity. I'll be the first human to know. Your radio transmits the words, but they don't propagate outward. They propagate inward, toward the singularity, joining you on your final approach. The photons carrying your voice will reach the singularity at the same moment you do. 5 seconds remaining. The tidal forces are extreme now. Your body is no longer intact. Your limbs have separated from your torso. Your cells have ruptured. You're a cloud of biological matter, still organized enough that some neurons are firing, some electrical patterns are propagating, but no longer recognizable as a human being. And yet, somehow, you're still experiencing something. The patterns of consciousness don't require an intact brain. They're substrate-independent emergent properties of information processing. As long as there's structure, as long as there's organization, there's something like awareness. 3 seconds remaining. You're wondering if this is what death feels like? Not the sudden cessation of biological functions, but this slow dissolution. This gradual loss of coherence. Your memories are fragmenting, your sense of self is dissolving. You can't remember your name. You can't remember why you're here. You can only feel the pull, the inward motion, the approach of something vast and final. 2 seconds remaining. The quantum effects are becoming important now. At the scale of your dispersed particles, at the extreme energies present this close to the singularity, the classical physics that governed your fall for the past 5 hours is breaking down. Your particles are behaving probabilistically, their positions and momenta becoming uncertain, their wave functions spreading out and overlapping. You're becoming quantum. Your existence is transitioning from a classical state, a definite position, a definite trajectory, to a quantum superposition of possibilities. You're here and not here, falling and not falling, existing and not existing. 1 second remaining. The singularity is right in front of you, or right ahead in time, or both. The distinction has lost meaning. You're at the boundary where the equations produce infinities, where density becomes infinite and curvature becomes infinite, and all the quantities that physics uses to describe reality diverge to meaninglessness. And in this final second, you have a thought. Not a complex thought. You no longer have the neural structure for complexity, but a simple awareness, a final flicker of consciousness. This is what it means to fall into a black hole. Not the journey from the outside, not the 5-hour countdown, not the mathematics or the physics. This moment, this dissolution, this transition from being to not being, from existence to whatever comes next. Zero. You reach the singularity. And then the answer is, we don't know. Classical general relativity says your particles are crushed to infinite density at a geometric point of zero volume. Quantum mechanics says something prevents that, some effect at the Planck scale that replaces the singularity with a quantum structure. String theory says the singularity is smoothed out into an extended object in higher dimensions. Loop quantum gravity says space-time itself becomes discrete, preventing the infinite collapse. But we don't know which, if any, of these theories is correct. We don't know what happens at the singularity because we can't observe it, can't test it, can't measure it. The event horizon ensures that whatever happens at the center stays at the center, hidden forever from external observation. What we do know is that the countdown ends, the timeline terminates. Your journey from the safe zone to the singularity, 5 hours and 15 minutes of falling, experiencing, observing, and ultimately dissolving, reaches its conclusion. Whether that conclusion is annihilation or transformation or something we haven't imagined, the question, how long would it take you to fall into a black hole, has been answered. 5 hours from the point where escape became impossible to the event horizon. 5 more minutes from the event horizon to the singularity. A total of 5 hours and 5 minutes from the beginning of the countdown to the end, but those are just numbers, durations, clock ticks. The real answer is more complex. From your perspective, it takes 5 hours and 5 minutes of subjective time, 5 hours of watching the universe compress and redshift, 5 minutes of experiencing the interior, the darkness, the final approach. Every second of that time is real, is experienced, is lived. From an outside observer's perspective, it takes forever. You never reach the event horizon. You remain frozen at the threshold, an image slowly fading over the lifetime of the universe. From their viewpoint, the question, how long does it take, has no answer, because the event never completes. And from the universe's perspective, if we can speak of such a thing, it's instantaneous and eternal simultaneously. The matter that falls into a black hole is removed from causality, erased from the future light cone of the outside universe. It happened and is still happening and will always be happening, frozen in the eternal now of the event horizon. So how long would it take you to fall into a black hole? 5 hours and 5 minutes, forever, instantly. All of the above, depending on who's measuring and from where they're watching. This is the final truth about black holes. They're not just objects in space. They're paradoxes in time. They're boundaries where our intuitions about causality, duration, and existence break down completely. They're places where the universe reveals that time itself is not what we thought it was, not a universal river flowing at the same rate for everyone, but a local phenomenon, a personal experience, something that can stretch and compress and terminate depending on where you are and what you're falling into. And if you ever find yourself falling into one, If the countdown ever begins, you'll have 5 hours to contemplate that truth, 5 hours to watch the universe transform around you, 5 hours to feel the pull of gravity, the stretch of tidal forces, the weight of inevitability, 5 hours until the event horizon, 5 minutes until the singularity, and then whatever comes next. The clock is ticking. The countdown has always been ticking. For every object near a black hole, for every particle in the accretion disk, for every star in an unstable orbit, the countdown is running. Some have years left, some have days, some have seconds, but all of them are falling. All of them are approaching the threshold, and all of them will eventually reach zero. Because that's what black holes do. They wait with infinite patience, they pull with inexorable force, and they consume everything that crosses their boundary, adding it to the mass inside, preserving it in the frozen image at the event horizon, and destroying it at the singularity. They are the universe's ultimate countdown clocks, marking the time until matter reaches its final destination. And the answer to how long it takes is always the same, exactly as long as it takes for you to travel from where you are now to where space-time itself ends. For a stellar mass black hole, 5 hours until death by spaghettification, a few more minutes until your atoms cross the horizon. For a supermassive black hole, 5 hours until the horizon, 5 minutes until the singularity, with consciousness persisting somewhere in between. For you, reading this, infinite time, because you're not falling and hopefully never will be. But if the countdown ever starts, if you ever find yourself drifting toward that infinite darkness, now you know. Now you understand the timeline. Now you can mark the phases, the deceptive calm, the increasing tidal forces, the approach to the horizon, the crossing of the threshold, the final descent to the singularity. You know how long it would take. And you know that once the countdown begins, there's no stopping it. The clock ticks forward 1 second at a time until it reaches zero. And then, in the words of every countdown that has ever reached its conclusion, time's up. But let's sit with that ending for a moment longer, because there's something we haven't fully addressed, something that might be the most disturbing aspect of this entire timeline. What happens to the information you fell into the black hole? Your body, your memories, your thoughts, the specific arrangement of atoms that made you uniquely you, all of it crossed the event horizon and reached the singularity. From the universe's perspective, you've been erased, but the laws of quantum mechanics say that information cannot be destroyed. Every particle, every quantum state, every bit of data about your configuration must be preserved somewhere, somehow. This is the black hole information paradox, and it's been troubling physicists since Stephen Hawking first identified it in the 1970s. Here's the problem. When you fall into a black hole, you carry information with you. The exact positions and momenta of every particle in your body, the quantum states of every electron, the precise configuration of every molecule. This information crosses the event horizon with you and reaches the singularity. According to classical general relativity, that information is destroyed at the singularity, gone, erased from reality. The infinite density and zero volume of the singularity crushes everything down to a point where quantum states lose meaning and information ceases to exist. But quantum mechanics says this is impossible. Information is conserved, always. In every physical process we've ever observed, information can be scrambled, encoded, hidden, but never truly destroyed. If you burn a book, the information isn't lost. It's encoded in the smoke particles, the heat radiation, the ash. With perfect knowledge and unlimited computing power, you could reconstruct the book from the remnants. So where does your information go when you fall into a black hole? One possibility is that it's preserved at the event horizon. As you cross the threshold, quantum effects create a holographic encoding of your information on the two-dimensional surface of the horizon. You, the three-dimensional you, get destroyed at the singularity. But your information, the complete quantum description of everything you were, gets imprinted on the horizon like a hologram on a screen. This is the holographic principle, and it's one of the most profound insights in modern physics. It suggests that our three-dimensional reality might be a projection of information encoded on a two-dimensional boundary. You experience yourself as a three-dimensional being moving through space, but fundamentally, you might be information written on a distant surface. If this is true, then when you reach the singularity at the end of your 5-hour and 5-minute fall, you don't simply cease to exist. You persist as information on the event horizon, not conscious, not experiencing, but preserved in some form, your quantum state encoded in the microscopic structure of the horizon. And here's where it gets stranger. Hawking radiation suggests that black holes eventually evaporate. They emit thermal radiation due to quantum effects near the horizon, and over astronomical timescales, they slowly lose mass and shrink. For a supermassive black hole, this process takes 10 to the power of 100 years, a number so large it's almost meaningless. But eventually, the black hole will evaporate completely, releasing all its mass energy back into the universe as radiation. The question is, does that radiation carry the information that fell in? Does the Hawking radiation that emerges from a black hole 10 to the power of 100 years from now contain the encoded quantum state of everything that ever crossed the horizon, including you? Recent developments in quantum gravity suggest the answer might be yes. The information isn't destroyed. It's scrambled, encoded in complex correlations between Hawking radiation particles, and eventually emitted back into the universe over the course of the black hole's evaporation. Your information, the quantum description of who and what you were, would emerge, particle by particle, over trillions upon trillions of years. Not as you, not as a conscious being, not as anything recognizable, but as information preserved in the quantum correlations of radiation particles scattered across the universe. So, the final answer to how long would it take you to fall into a black hole might have an additional phase we haven't considered. 5 hours until the event horizon, 5 minutes until the singularity, and then 10 to the power of 100 years until your information is released back into the universe through Hawking radiation. The countdown doesn't end at 0. It extends beyond your death, beyond the death of stars, beyond the death of galaxies, into the deep future when the universe is cold and dark and nearly empty. And at the end of that unimaginable span of time, something of you, not your consciousness, not your identity, but your information, returns. This raises a philosophical question. If your information persists, encoded on the horizon and eventually emitted as radiation, are you really destroyed? Or are you transformed into a different form of existence? There's no consciousness in Hawking radiation, no experience, no thoughts or feelings, but the information is there. The complete quantum description of every particle that made up your body, preserved in principle if not in practice, scattered across the cosmos as the black hole slowly evaporates. Some physicists speculate that in the far future, an advanced civilization with technology beyond our imagination might be able to collect that radiation, decode the correlations, and reconstruct the quantum states of everything that ever fell into the black hole. They couldn't bring you back. Consciousness isn't just information, it's information organized in a specific dynamic pattern. But they could, in theory, know everything about you. Every thought you ever had, every memory, every quantum detail of your existence at the moment you crossed the horizon. You'd be archaeology, data from the ancient past, preserved in the most secure archive the universe has ever created, a black hole's event horizon. But that's speculation. What we know for certain is that the timeline of falling into a black hole doesn't end when you reach the singularity. It extends forward through the entire remaining lifetime of the black hole and possibly beyond. From one perspective, you fell in and died in 5 hours and 5 minutes. From another perspective, you're still there, your information encoded on the horizon, waiting to be released over time scales that dwarf the current age of the universe. Both timelines are real, both are true, and both are part of the answer to how long it takes to fall into a black hole. The countdown to the singularity, 5 hours and 5 minutes. The countdown to information release, 10 to the power of 100 years. And the question of which timeline is yours, which one represents the true duration of your existence, has no definitive answer. You are both the person who died at the singularity and the information pattern encoded on the horizon. You exist in both timelines simultaneously, separated by eons but connected by the quantum threads that link past and future. This is the final paradox of black holes. They're not just objects that warp space and time. They're objects that warp existence itself, creating multiple parallel truths about the same event. You fall in. You never fall in. You die at the singularity. You persist as information on the horizon. You're destroyed. You're preserved. All of these statements are true, depending on your reference frame and your definition of existence. So, when someone asks, how long would it take you to fall into a black hole, the complete answer must include all the timelines. From your subjective experience, 5 hours and 5 minutes from the safe zone to the singularity. From an outside observer, infinite time, as you never quite reach the horizon in their reference frame. From the perspective of quantum information, 10 to the power of 100 years until your encoded state is released through Hawking radiation. And from the perspective of the universe itself, an instant and an eternity, a beginning and an ending, a transformation from one form of existence to another. The clock is ticking on all these timelines simultaneously. Right now, at the center of our galaxy, matter is falling into Sagittarius A star. Some of it crossed the event horizon yesterday, some will cross tomorrow, and all of it is simultaneously frozen at the threshold, destroyed at the singularity, and encoded on the horizon waiting for release in the incomprehensibly distant future. The countdown never stops, it just transforms, branching into multiple futures, each one as real as the others. And if you ever find yourself falling into a black hole, you'll experience all of them. The 5-hour descent, the instant of crossing, the eternal freeze at the horizon, and the slow information release across deep time. You'll be all of those timelines at once. Because that's what happens when you fall into a black hole. You don't just fall through space, you fall through time itself. And the answer to how long does it take becomes a question about which aspect of time you're measuring. Experiential time, coordinate time, or the deep time of information preservation. All of them are valid. All of them are true. And all of them are part of your timeline from the moment the countdown begins to the moment, or eternity, when it finally ends.